Hi everyone, welcome to week 4 videos. Before we get started, just a little bit of housekeeping. Go ahead and click on this file .getignore. If you've been seeing this file that's been annoying you called .ds_store, that's just a data file that's kind of an artifact of how Macs work. Whenever you navigate by hand through all these folders, it creates this kind of annoying file called .ds_store that doesn't really matter. But it can clog up your Git folder and your Git tab up in the right-hand corner and be kind of annoying. So the easy way to fix that to make Git stop noticing this file is to add it to our gitignore file. And what gitignore does is it's basically just a list of files and it tells Git, hey, don't worry about these files. Don't try to sync them to and from the cloud. So we're just going to save this. And when we do, we added this line .ds_store. Now we're going to see this box where our gitignore file is updated. We can commit this and say added .ds_store to the gitignore file. And now, ta-da, you won't be bothered by that annoying little pop-up anymore. Um, so we're going to go ahead and close that and continue with our week 4 selecting, filtering, and piping. This is part 1 of what we're going to be learning this week. So this week we're going to be doing our introduction to the tidyverse package. The tidyverse package is an umbrella package that includes several packages we're going to use this quarter called tidyr, dplyr, ggplot, and tibble, and some other things. We'll talk about those. But the first thing you're going to want to do if you haven't done this ever before is install .packages in quotes tidyverse. And you're going to go ahead and command enter on that. And that's something you only need to do once ever, not every time you open up the script, just once. So why are we doing this and why are we installing this tidyverse package? Well, we've learned about bracket subsetting, how to use brackets after an array to find certain elements within that array, etc. But those brackets, especially when you have two-dimensional data, can be really difficult to use, and it's easy to make mistakes when trying to use those that subsetting notation. So instead, dplyr is a package we're going to use, which is great for data table manipulation. It has really straightforward function names that do the same thing. And then tidyr, meanwhile, is a package that is going to help us switch between data formats. For instance, I have a project right now where I'm working with some data where there's a bunch of farmers that we have survey data from, and each of those farmers has a bunch of different crops. And then we have information on each of those different crops. So you can imagine some analysis where I might want each farmer to have their own row to be considered as their own observation. But then you can consider another scenario where I might want that analysis to have each farmer's individual crop as its own observation. So for instance, farmer 1, crop 1, the next row is farmer 1, crop 2, moving on. So tidyr is a package that helps you manipulate and shift your data set to accommodate those different needs. All right, so more benefits of tidyverse are it has predictable results. Sometimes those base functions in R that just come right with R that you don't need to install, they can have varying results based on what data type you enter into them. Also, tidyverse is great for new learners because its syntax is more consistent and understandable. And finally, it avoids hidden arguments. Sometimes functions in base R have hidden arguments in defaults. So if you remember back in week 2 when we were learning about the log function, well, the default for base for the log function is base E rather than base 10, which might not be intuitive. So that's just a simple example, but there's other base R functions that have surprising defaults. So tidyverse can help avoid some of those things by making everything more explicit. Okay, so after you're done installing the package, you might have to click yes a couple times. If it asks you to install all, just go ahead and install all the packages and all the dependencies. Now we're going to load the package. You might have to restart R after installing tidyverse and before installing this library, or before loading this library, excuse me. Okay, so we've loaded tidyverse. And now we're going to work with our data set. So if you look in your file organization over here, you should have a folder called data. If you open this up, it has a few CSV files. Those are comma separated value files, has everything all nice and tidy. So we're going to read one of those in using read_CSV, which is a function that is available to us because of the tidyverse package. Okay, so let's say we want to know what's in this magical surveys data file we just read in. There's a couple ways to do that. Number one, you can click over here on your environment, which pops it up in a new window. Equivalently, you can type in to the console or on your script view surveys, and that does the same thing. It opens it up in a new window. Uh, Alternatively, you can look at STR of surveys, which gives you an overview of the structure right in your console that is a little bit more readable and doesn't take up as much space. So for instance, you can see each of these dollar signs refers to a different column. So there's a column called record ID. It's a numeric column. It stores numeric data. Same thing with month, day, year. Those are all numeric. Then we have species ID, which is a CHR, which stands for character. In other words, a series of letters. So each of these stores a word or phrase. And then we have sex. We have the length of this species back foot. We have this weight of this individual and the genus. And a bunch of other columns that it says ... and or actually the ... is referring to there's many different observations, there's many different rows in this data, and it's not going to print out all 34,000 rows. It's just going to print out the first few to show us what the data look like. And then finally, it will show us what type of data is being stored by each of these columns. So it's going to give us first some examples of different data cells, different observations for each of those columns, and then what type of data those are. And that's it. So it'll also tell you that under this, the specs of the table, it's 34,786. That's the number of rows, and there's 13 columns. So STR is a very useful function for just getting the overview of a new data set. Okay, so let's practice selecting columns. Let's say you don't want all 13 of these columns, you just want the year. So we're going to use this function called select. The first argument is the data file, because select has to know what data we're trying to subset. And then after that, you list every single column that you want to keep. So right now, you're only selecting the columns month, day, year. So if you want to predict how many columns will be in this resulting data set, month, day, year, the answer is 3. There's 3 variables, 3 columns left in month, day, year. So next, what if instead of selecting certain columns, certain data types that you want to run a sifter, a filter through all of your observations and only keep certain observations that meet logical criteria, like the logical statements we've been learning to make in week 2 of this class. So that statement is called filter. This is a function that you can use to filter out specific rows that meet a criteria. So we'll start with our surveys data set again. And this time we're going to use a logical condition. We want the year column in our surveys data set to be 1981. So we only want to keep the entries that have the year 1981. So let's practice doing that. It will print out in the console. Now it's a tibble with 1,400 records, which is much less than the 34,000 records we started with, and it still has all of our columns, all of our data types in it. So notice that in our environment, we don't have a new variable with the results of this year filtering. That's because we didn't assign it to a new variable. We just ran it. So if you actually want to manipulate this data set and do stuff with it, you would have to, year 1981, we would have to create a new variable. And assign it to this output. Now it shows up because we've taken this output and we've finally assigned it to a variable. Note, you can't name a variable starting with a number. That's a bad idea. Okay, so what if we didn't just want 1 year, we wanted multiple years? First, let's practice filtering for results that occur from 1981 to 1983. We can run this. The output will show up in the console just so we can see what it looks like. And it'll only show the first 10 rows in the output. And this has 5,000 observations. So more observations than just 1981, which makes sense. It's always good to do a sanity check and make sure that your results from filtering and selecting make sense. Okay, so we used that function in percent as a bucket search. We wanted to say, hey, out of all the observations, I want everything where the year is found somewhere in this list of 81, 82, 83. So let's have a review from week 2 of this quarter. Why should you never do this, which is filter surveys year equals concatenated 1981, 1982, 1983. Equivalently 1981 colon 1983, which is the same thing, just like we had up there. So why should you never do that? Well, let's look at the results. So remember when we did percent in percent, that was 5,000 results. So let's see, do you think this will be the same or will it be different? We're going to run this and notice there's a warning message. The longer object length is not a multiple of the shorter object length. Okay, so that's telling us that's a big clue for why this is not going to have our desired output. So if we go up, there's only 1,685 results. So this has 1,685 results compared to what we ran up there, which was 5,033 results. So why do those not have the same number of results? Well, that's because percent in percent does bucket matching. It goes to this bucket with the years 1981, 82, 83. It picks up a year that it found in the observation. It says, is this year in this bucket that contains 1981, 82, 83? It's 1982. Oh, great. We keep it in. But that's not what's happening here. When we say equals, and then we have a vector of values, that's index level matching. So that's taking the first column in the survey or the first row in the surveys saying, hey, does the year in that row equal 1981? Yes or no? Now let's go to the second row. Does the year of that row in surveys equal 1982? Because now we're on to the second element of our checking vector. Yes or no? And then it goes on to, does row 3 year equal 1983? And then it recycles back to, does row 4 equal 1981? And it keeps checking like that. So that's why there's fewer results, because row 2 is only getting checked for if it's 1982. Row 2 isn't getting checked for if it's in any of those years. So that's why there's about a third of the results, as we saw up here when we were checking every row to see if it matched any of those years. Okay, so if for some reason you should really never have to do that for most purposes, you should never really have to do this recycling. If for some reason you really need to do that, you should comment it very clearly in your code and explain why you're recycling. That's just a gift to your future self, so that your future self doesn't wonder about all the data that you lost in this process. Okay, so back to filtering by conditional statements. You can also filter by multiple conditions. For instance, Bigfoot with weight. That's our new variable we can assign. If we want to filter our data frame surveys for 2 conditions, number 1, if they have a large hind foot, if the hind foot length is over 40, and additionally, we want to make sure that their weight is not NA. So we want to make sure that there is something listed in that weight cell. So Bigfoot with weight, we can run this, and even though there's multiple conditions, it will print out. There's 2,045 observations. So first, let's do a multi-step process. Let's say we want multiple filtering steps in our data survey. We'll start with surveys, and let's say we only want the small animals with a weight of less than 5. We can assign that to a variable called small animals. But the problem here is this is a little bit dangerous because now we've created an intermediate data frame that we need to remember to use in our next step. Because if we put surveys here in our next step instead of small animals, we would lose all the filtering that we just did in defining this new data frame. So that's kind of dangerous to do. Um, but just to show you an example, we're going to select from this data frame small animals. And let's say we only want 3 columns, the record ID, the plot ID, and the species ID, which is all the IDs in the data frame. We'll call this small animal IDs. Cool. Okay, so we created a new data frame called small animal IDs. But because that was kind of dangerous using this intermediate step, there's a better way, which uses nested functions. So we don't have to have a separate line of code with those intermediate steps. We can do it all at the same time. So instead of small animals, remember small animals was equivalent to just filtering surveys for a weight of less than 5. So instead of selecting small animals, we can just copy this whole filtering statement and put it in right there like it is on line 66, which is equivalent. If we run this, we get the same small animal IDs output. But this is a little bit clunky using nested functions. So the same process can be done using a pipe. So if you hit Command Shift M, now note that this function only exists within tidyverse. So if you don't have tidyverse loaded, you won't be able to use this pipe. Equivalently, there is a pipe in base R that looks like this. It's the vertical bar and a right arrow sign or a greater than sign. But a lot of people are more familiar with the tidyverse version of the pipe, which looks like percent caret percent or percent greater than percent. So we're going to use that in this class, but note that they are equivalent. So you can use whichever you prefer. But you'll be able to read our code a little bit better if you follow along. Okay, so this is what our pipe looks like. And instead of using this nested approach like we did in line 66, here, I'll make this a little bit bigger so you can see. Instead, we're going to use a pipe. We're going to put that filtering statement first, then put our pipe, and then have our selecting statement. So you always read a pipe from left to right, just like in a nested function, how like order of operations are evaluates from the inside out. Well, with a pipe, it evaluates from left to right. So remember how in the select function, we always needed our data frame to be the first variable? Well, when we use a pipe, it's the equivalent of putting an invisible variable right here, argument, that ports this whole entire filtering statement right before that first comma. So whenever you use a pipe, select is understanding that this filtering statement that you already did that happens before the pipe gets ported into the select function as the invisible first variable there. So that's why we don't need to, again, write the data frame that select is using because we already wrote it. It's this filtering thing. Okay, so what this will do is exactly equivalent to the nested function above. It evaluates the filtering first, and then it pipes that entire filtered data frame, which is basically in this case, the survey observations that have a weight of less than 5, it ports that into the select statement. Okay, so these are all equivalent ways of doing this. But we've used one pipe to separate the filter statement from the select statement, but we can actually use another pipe. So we can just use surveys. We can pop this out of the filtering statement and use surveys pipe filter. And just like before, when we use a pipe, it's understood that this surveys that we just wrote down is the invisible first argument in this filter statement. So what we've written here, surveys pipe filter of weight, is equivalent to filtering surveys, comma, weight. So this is just a more readable way rather than creating a bunch of nested parentheses, is being able to read the statement from left to right. Okay, so these are all equivalent. But when you use a set of piping statements, stuff can get really long. So this line of code is really starting to get off the page and creates a lot of scrolling and is very difficult to read. So let's learn how to use line breaks with pipes. Let's say we have surveys, pipe, filter, month equals 1, which is going to filter all the January entries in our data set. So one way to break this into multiple lines is to go right after the pipe. So this is a good option. Surveys, pipe, filter, month equals 1. So we can see that it created a tibble for us with about 2,400 entries. Versus this is not good. So if we create a line break right before the pipe, notice that we get this little X that says unexpected token. So what's happening here? Well, when we run this line of code that just says surveys, it goes, oh, surveys, I know what you want there. You want me to print out the entire surveys data frame with all 34,000 entries. But so it doesn't know that we're still wanting to do something with that surveys. So whenever you use a line break, you always want to break the line such that R knows there's no way that that line of code could be done because it's an improper line of code. So for instance, if we ran surveys percent greater sign percent or surveys pipe, and I highlighted that and ran, notice this plus sign. That's R saying, hey, that's not a complete line of code. There's something missing here, which means it's waiting for the rest of that line of code filter. So it knows that you can't end a line of a statement on a pipe. So notice when we try to create that line break, if we go after the pipe, it will create a tab for us. That's because it's like a paragraph. R knows that this is all part of the same paragraph, all part of the same line of code. Versus if we try to create a line break before the pipe, it'll just go right over to the far left edge because surveys by itself is a complete line of code. So it thinks that this is a totally separate totally separate line of code. So in summary, the line break rules are after an open parenthesis is fine, after a pipe is fine, after a comma, or basically anything that shows the line is not complete yet. And you can check by seeing if R creates that paragraph break for you. For instance, if I go here, it creates an indentation. If I break after the pipe, it creates an indentation, or after a comma, again, it creates an indentation. So that's a sanity check for you. One final thing is, as a bonus for watching these videos and for going on our repository to look at the sample code, you will now see a folder of cute rodent photos, which will be updated throughout the quarter. These are photos of all the species that are in our data file that we will be working with this quarter, like it's the same data file we were working with in this script up here. So that will be updated throughout the quarter. And as a bonus for watching this video, here's a couple of cute rodent photos. This is the Paramyscus leucopus. Let's see if it opens up there. I don't know if you can see that, but if not, check out my repository on GitHub. All right, I'll see you in class. Bye.